Hello, my name is Irena Spasic. I'm a professor in computer science at Cardiff University, UK. I'll give a short presentation based on our recently published paper, Patient Triage by Topic Modeling of Referral Letters. However, I will be focusing only on one aspect of this study, and it is concerned with measuring interpretability of automated outputs in clinical text mining. My presentation will start by motivating the problem in a wider context before introducing an experimental protocol that we developed to assess interpretability of topic modeling results. Clinical decision support systems are used to improve healthcare delivery. They use computerized models to convert data into information. Information is then used to support a clinician in making some decision regarding a patient. For instance, signs and symptoms can be mapped onto plausible diagnosis, which a clinician can then use to suggest an appropriate treatment. Traditionally, a computerized clinical knowledge base is used to transform data into information in a series of algorithmic steps. Here the model is explicit, which makes it straightforward to trace individual steps in this process. This provides an unambiguous explanation of how X was mapped onto Y. But for such a model to be built, clinical knowledge, which can often be tacit, needs to be elicited from domain experts. And this is a well-known bottleneck of rule-based approaches. This is why clinical decision support systems are increasingly relying on machine learning. Machine learning can leverage vast amounts of data and patterns therein which may not be apparent to humans due to their volume and complexity. Training data are used to build a model, which in turn is used to transform data into information. Some machine learning methods produce explicit models such as decision trees, which can be used to retrace the path from data to information. However, more often than not, machine learning produces black box models that cannot be easily opened up to observe its internal processes that are used to transform data into information. If we put such models back into clinical decision support scenario, we can see that their outputs are used by various stakeholders, most importantly clinicians and patients, to support their decision making. In such a setting, the stakes are obviously very high, as such a decision can literally mean a difference between life and death. It is therefore understandable that the stakeholders need to have a trust in machine learning models that are used to inform their decisions. One way to build a trust in the machine learning models is to use some metrics such as accuracy and optimize the model with respect to the chosen metric. One advantage of machine learning is that it can be used to build such models rapidly, providing that adequate training data are available. Unfortunately, these models tend to lack transparency, meaning that their logic cannot be easily explained. And it is actually explainability, in addition to high performance, that is the key for the buy-in from all stakeholders in a clinical setting. In the literature, explainability is often used synonymously with interpretability. In its strictest sense, it can be interpreted as the ability to reenact the results. In general, explainability is defined as the extent to which the internal logic of a machine learning model can be explained in human terms. Various definitions of interpretability have been proposed. Some are linking interpretability to the extent to which a cause and effect can be observed in a system. Such a definition is making it very hard to properly distinguish interpretability from explainability. Others define interpretability as the extent to which a given learning model makes sense to a user, but such a vague definition is practically inoperable. For the sake of clarity, but running a risk of oversimplifying the matter, I actually prefer to apply interpretability to the actual outputs of a machine learning model. And in this presentation, I will be focusing on interpretability in this narrow sense. Let me clarify these notions of explainability and interpretability using this simple example. We do not need to know how electricity is generated in order to use it safely. In this context, explainability answers the question how, while interpretability answers the question what. Let us focus on the latter for a moment. It may not be obvious why we would need to interpret automated outputs. For example, in supervised learning, the class labels are predefined, so we already know what they mean. We are simply using the model to assort the data into well-defined categories. We may not necessarily be able to explain how exactly the data are classified, but we can interpret the system's suggestions and use them to support decision-making. However, the training of supervised models requires large amounts of data to be annotated. In a clinical setting, this may be a problem as annotations cannot be crowdsourced for at least two reasons. First, it requires clinical expertise which is not readily available online. And the second one is related to privacy concerns surrounding the sensitive nature of the data. These issues are gently nudging the clinical text mining community towards unsupervised methods, which avoid the need for manual annotation altogether. Another reason to rely on supervised learning is that many clinical applications, such as patient safety, rely on discovering so-called unknown unknowns. So defining a closed class of categories is not only difficult, but also not entirely appropriate. On the other hand, unsupervised learning can identify latent patterns in the data that may not be apparent a priori. But once uncovered, these patterns are not always easy to interpret. For example, clustering techniques can be used to discover coherent groups of objects, but it is not necessarily obvious what these groups really mean. This leads me to topic modeling as another set of unsupervised learning techniques. It groups documents into topics which can also overlap. Each topic is associated with a set of keywords which can be used to interpret the topic. For example, if we are dealing with referral letters of patients with knee problems, then one topic may be referring to obese patients. Each referral letter can then be mapped automatically to one or more topics, and if we know what each topic means, then we can also automatically direct or redirect patients along their pathway. This particular application is motivated by a genuine problem in healthcare. Over 30% of patients with hip and knee pain end up following a suboptimal pathway. What we mean by an optimal pathway is a pathway that results in the right treatment at the right time. What happens in practice, for example, is that some patients are referred to an orthopedic clinic only to be redirected to advanced physio rather than referring them directly from primary care. Such cases represent not only a considerable waste of healthcare resources, but also affect the health outcomes for many patients. As I mentioned previously, we use topic modeling to deal with this problem. To fit this into clinical decision support framework, we have a set of referral letters as our data. Latent Dirichlet allocation is used to map each referral letter to topics, which in turn are used to refer patients to most appropriate treatment, which represents a decision. To investigate whether such an approach would be acceptable in clinical practice, we focus on a problem of assessing the interpretability of individual topics. Each topic is associated with a set of keywords, and we wanted to examine whether clinicians can interpret these topics as cohorts of patients who share common characteristics or experience, such as medical history, demographics, and possible treatments. For example, we could differentiate between obese patients, elderly patients, those with sports injuries, etc. But remember that we are dealing with an unsupervised learning method, so that means that we do not know in advance what categories of patients these topics represent. To assess human interpretability of a topic, we may, for example, present a clinician with the corresponding keywords and ask them to describe the topic in their own words. We can also ask them to rate how confident they are that the description is correct. In this scenario, we assume that high confidence implies that the topic is relatively easy to interpret. But this is where we encounter a problem, namely high confidence does not imply that the corresponding interpretation is a correct one. This raises another question. How do we know that the given interpretation is actually correct? This is a question of validity. As we are dealing with an unsupervised method, the problem here is that there is no ground truth, no gold standard that we could use to test whether the answer is correct. Therefore, we cannot check directly if it is correct or not. So what do we do? Given the lack of a gold standard, we resort to testing reliability rather than validity. Instead of approaching a single clinician, we could approach two clinicians and perform the same topic interpretation task independently. Then we can ask the following question. Are experts consistent with one another? In other words, are they consistently making the same interpretation? Such an approach is commonly used to measure inter-annotator agreement when gold standards are created. Chance-corrected measures, such as Cohen's kappa coefficient, can be used to measure the agreement. On a scale from 0 to 100, the agreement can then be classified from slight to perfect. We can now assume that high reliability implies validity. In other words, if two clinicians independently came up with the same interpretation, then it is more likely that such an interpretation is in fact correct. Cohen's kappa coefficient can be used for different types of data. To calculate the agreement, we need some means of comparing two data items. However, comparing two text descriptions is not straightforward. To deal with this problem, that is, to compare the similarity of two text descriptions, we came up with the following protocol. A topic described by a set of keywords is presented to two clinicians. Independently, each clinician describes their own interpretation of the given topic. Once this task is completed, they exchange their descriptions. They are then asked to compare the two descriptions and rate the similarity independently. At that point, we can measure the agreement between the ratings using Cohen's kappa coefficient. Note that the high agreement also covers cases where two clinicians agree to disagree. That is, when both agree that the topics are dissimilar. Therefore, both average similarity and inter-annotator agreement should be used simultaneously to assess interpretability. Let me show you a few examples from our study. Here we can see that both clinicians, using different levels of details, describe patients with injuries of knee ligaments who experience the associated symptoms such as swelling, instability, and locking, and most prominently effusion. Both clinicians agreed that the descriptions were indeed very similar. In another example, we can see a cohort of hip patients experiencing degenerative changes. To some extent, both clinicians agreed that their descriptions were similar. In the last example, we can see how a given set of keywords may have led to two different interpretations. Here, both clinicians agreed to disagree. It is therefore important to take into account similarity as well as confidence and inter-annotator agreement when measuring interpretability of topics. Similarity is the key measure here. The higher, the better. The other two measures are used to account for the guesswork. Agreement measures not only the discrepancy between the two clinicians, but also corrects for the chance agreement. Confidence, on the other hand, accounts for inherent ambiguity. The lower the confidence, the higher the ambiguity. Overall, we can measure interpretability from multiple angles to get a full picture. In practice, we use the 5-point Likert scale to measure confidence and symmetric 6-point Likert scale to measure similarity. We then use weighted Cohen's kappa coefficient to measure inter-annotator agreement. Further details about this study can be found in this recently published article, in which we have demonstrated that by and large, latent topics discovered using LDA can be interpreted by clinicians as cohorts of patients. This paper also contains other technical details on how we ensure high interpretability of topics by fine-tuning the number of topics using topic coherence measures and integrating external knowledge sources such as the UMLS into the topic modeling framework. On that note, I will finish this talk. Thanks for listening.